Hi, I'm Martin and welcome back to part 2 of this video series about Cynthion, the USB multi-tool from Great Scott Gadgets. In the last video I introduced you to the Cynthion hardware and I showed you how you could use Cynthion as a sniffer to capture data between the PlayStation 5 controller and the console, and how to reverse engineer what's going on in that data and how it's structured. So if you missed that, you may want to go back and check that out first. And as a reminder, our goal in this series is to use Cynthion to emulate the PlayStation 5 controller, and then we're going to use that emulation to try to do a tool-assisted speedrun on the console. So in this video we're going to start on that emulation. We're going to take what we learned from capturing the controller traffic, and I'm going to show you how you can use that information to make Cynthion pretend to be a PS5 controller. And the really great thing about this is to get started with this, you don't need to write any firmware, you don't need to write any gateware, you don't need to know how to develop for the FPGA that's in here. All we're going to use is Python. And the reason that we can do that is a really cool project called Facedancer. Now, I'm going to start by explaining what Facedancer is and how it works. Let's start first with some basics. So in USB we talk about hosts and devices. The host is the thing that you plug devices into, like it's a computer or a console. It's the thing that's in charge. On a USB bus you can have lots of devices, but only one host. And the devices are everything else, like keyboards, mice, flash drives, anything that you plug into a USB port. And all USB communications are controlled by the host. The devices can't communicate except when the host tells them to. So for example, when the host wants to send data to some device, the first thing that happens is it sends an out packet. Now, this kind of packet is called a token, and it has the device address and an endpoint number, so it tells the device, hey, the next data is for you. And just after that it sends a data packet, and that's what carries the payload. And then immediately after that the device has to respond to confirm whether it received that data. And usually what it will send is ACK, which means, okay, I got that data. Now that sequence of 3 packets, that's called a transaction, and it has tight timing requirements. Each of those packets has to follow the previous one within a few hundred nanoseconds. So at this level of the protocol, really everything is happening in hardware. You wouldn't usually write code to handle USB at the packet level, and certainly not in something like Python, because it just wouldn't be fast enough. Now, the data being transferred here could be anything, but for example, let's say this data is some kind of prompt from the host, like it's asking the device for a password to authenticate itself. You might think that's an odd thing for it to do, because like your computer doesn't usually ask your mouse to prove who it is, but actually something like this is going to come up with the PS5 controller. There's some authentication going on there, which we'll come back to. But the point is, the host has sent some prompt or command to the device, and it's going to expect a response. So let's look at how data flows the other way. Now when the host wants data from the device, it sends an in packet. So this is another kind of token, again with a device address and an endpoint number, and so it's asking this particular device, hey, do you have data for me? And now once again there's tight timing requirements. The device has to answer within a few hundred nanoseconds, which is obviously not a lot of time. Maybe the device doesn't have data ready. So even if the device knows that password, it may not be able to load it that quickly and have it ready to send. So the USB protocol allows the device to respond with NAC, which means basically, I'm not ready yet, ask me again later. And this is what lets us decouple the low-level protocol, where everything happens in hardware with these nanosecond timings, from how we handle USB in software, where things can just take, well, however long they take. Now, let's say we want to emulate this device. We could do that by writing some custom firmware for some platform that has the USB hardware, but it's really fiddly. So the idea of Facedancer is that we have a device that's like a secret agent for us. Like we've got an agent who's sitting in a meeting wearing an earpiece, and outside the building we've got a team sitting in a van who are listening in and telling the agent what to say. So when the host asks for the password, the agent asks the team in the van, and they're like, stand by, we're just going to hack the Gibson and find that password for you, but it's going to take us a while. And the agent has to have some way to buy us time while we get the answer. And that's what the NAC does. Now the host can keep asking for data, but the device is allowed to keep saying NAC for basically as long as it wants. So you get these transaction sequences that are just like in NAC, and then in NAC, and you can do this hundreds or even thousands of times. The host is just polling the device. You can time out here. The host's allowed to give up, but usually you're going to find that the timeout on the host side is going to be quite long, because in practice the real device always applies pretty quickly, so nobody ever spends time like fine-tuning that timeout in the driver. It's usually just like a second or something like that. So as long as you can respond within that amount of time, the host will accept it no matter how many times it has to poll the device to get there. So eventually this team finds the password, tells it to the agent, and the next time the host sends an in packet, this time the device is ready, and instead of a NAC it can send a data packet. And the host will acknowledge that data packet, and now we're done. So how this works in practice is that your team in the van, that's another computer, and it's running your Python code using the Facedancer library. And the secret agent is some firmware that's running on some platform that provides the USB hardware which actually is going to sit on the bus and speak the low-level protocol with the nanosecond timings. Now, the Facedancer library supports several different hardware platforms for doing this, where people have written firmware that lets you use them with Facedancer. Each of those has some kind of control interface that serves as the back channel that you control it over, and these different control interfaces are supported by different backends in the Facedancer library. So that's how all this fits together on the software side. Now, something I want to address here is obviously there's a latency cost here, right? It's going to take some time for that message to get to the Python code. It's going to take some time for that Python code to respond, and those delays are probably going to vary a lot as well. So it's not going to be a great solution if you're trying to do something where the response is really timing critical. And if we want to speedrun a game, that's going to be timing critical, right? Well, actually not really. This is still a viable approach, because in practice we're going to be assembling our control inputs in advance. We're just going to be replaying sequences of inputs to try and do this tool-assisted speedrun. So as long as we can give those inputs to our agent device in advance, when the host polls for controller data, it's going to be able to supply that immediately within those nanoseconds, because it's already got that buffered up in the hardware. Now, Facedancer has been around for a while, and maybe you've heard about it before, but I want to bring you up to speed on how its capabilities have evolved over the last few years. So this was originally developed in 2012 by Travis Goodspeed. He did all of the original hardware, the software, the firmware for what's basically the first generation of Facedancer. Now that supported USB full speed, which is 12 megabits per second, but there was a bottleneck on the control interface, because that was serial and is like 100 times slower even than full speed USB, so you really couldn't do anything that needed any significant data rate with it. And it was limited to 2 inbound data endpoints and 1 outbound, plus the control endpoint, because that was the hardware limitation in the PHY. That's how many buffers it had for the endpoints. So this was a really useful tool, but there were a lot of devices that you couldn't emulate with it, either because you couldn't go fast enough or because you didn't have enough endpoints. Now, Philip Terwin adapted this to run on a Raspberry Pi with the Raspdancer hat board. So you had SPI to the PHY at 26 megabits per second, which took away that bottleneck, but you still had the other limitations. It's still full speed with just this handful of endpoints. In 2017, Kate Temkin and Dominic Spill, working at Great Scott Gadgets, released Facedancer 2. This was a new version of the project with a new API, and they added support for GreatFET, which is another Great Scott Gadgets product. You could control this over a high-speed USB link, but it's still full speed on the target side. It had more endpoints, like 3 each way, but it's still a constraint on what you can emulate. And then in 2024, we got 2 new platforms, both of which support high speed on the target side. Firstly, there's Hydradancer from Quark's Lab. This is based on the Hydra USB 3 board by Benjamin Vanu. This is super speed on the control interface, but it's still limited to 5 endpoints each way by the PHY. And then finally there's Cynthion, which is high speed both interfaces, and the really nice thing here is that because the whole USB stack is in Gateware, we don't have any hardware limits on the number of endpoints now. You can set up as many as the protocol allows, which is 15 each way. Now, we released Cynthion support in Facedancer version 3. That work was all led by Antoine van Gelder at GSG. And we still have the backends that support all the other hardware in this list. So if you have any of these devices, even one of the original GoodFET boards from Travis, you can still use it with the latest Facedancer. It will just have these limitations in the table. But we're going to use our Cynthion. So when we use Cynthion with Facedancer, that's going to be the device providing our USB hardware. We're going to use the target C port as where we emulate the device to the target host, and the control port as the control interface to connect it to our host running Facedancer. Now, making Cynthion work with Facedancer was a really big project, and I want to credit Antoine for this work, because remember, normally we have firmware that implements this, but there's no CPU, not a traditional CPU on Cynthion, it's just a big FPGA. So the first thing that had to be done to make this work is to put a whole RISC-V soft core in the FPGA and then build up a system-on-chip design using the Luna gateware to provide all the USB logic. So he's basically developed a complete chip design that exists specifically to implement Facedancer, but then rather than making that chip in silicon, synthesizing it into the FPGA. So that system-on-chip runs the firmware that he wrote, which is called Moondancer, because it's combining Luna with Facedancer, and of course because friendship is magic, and Moondancer is written in Rust. So this is a really neat solution, and also if you want to, you can write your own firmware for this system on chip, and that's one of the ways that you can develop for Cynthion now, and we have examples of that for both C and Rust. And Antoine has a great blog post about all this work, which you can check out on the Great Scott Gadgets site. So wait, I've probably made all this sound quite complicated, but we've packaged everything to make it really simple for you to set up. There's full instructions in the Cynthion documentation, but if you already have your Python set up, then it's really just two commands. Firstly, just install the Cynthion and Facedancer packages from PyPy, and then use the Cynthion command to tell it to load the gateware and firmware onto your Cynthion. Now we've just released Facedancer 3.1, which includes some improvements I've made to it since the last video, specifically to help with this PS5 project. There were some bits of the USB protocol that weren't supported well enough yet, so we couldn't do what I wanted to here. So if you want to follow along with what I'm doing in this video, just make sure that you've installed at least Facedancer 3.1. So let me show you just how easy this is to get running. All you really need is Python, and just check what version you have. You're going to need at least Python 3.10. I've got 3.12 here, which is fine. And what I'd recommend you do is set yourself up a virtual environment. You can do that with the Python venv module, and this sets up a sort of sandbox in which you can install Python packages, so it won't interfere with anything else on the system. I'll just call the environment venv. So that will set that environment up, and then you source the bin activate script to make that active. That looks slightly different on Windows, so check the documentation. But we're now in that virtual environment, and we can use pip to install the Cynthion package and the Facedancer package, and that will grab them from the internet. It will get the latest versions, and that doesn't take very long. Those are now installed, and so we should have the Cynthion command, and we can use this to set up our Cynthion. So I'm going to take my Cynthion here and plug it into this computer using the control port, and you can see it's popped up there in the USB messages from the kernel, and I can run Cynthion info, and we can see that it's there and it's running the USB analyzer bitstream. That's the one we were using with packetry. To run with Facedancer, we need to put the other bitstream on it, the one I mentioned with the Moondancer firmware and so on, and that's really easy. You just run Cynthion run Facedancer, and it will flash the Moondancer firmware into the flash. It will load the bitstream into the FPGA, and then that's going to re-enumerate, and you'll see it pop up as Facedancer, and that will also show up in Cynthion info. So now it's ready to use with the Facedancer library. Now what I'd like to do here is just show you a example script from the Facedancer examples. So I'm just going to clone the Facedancer repository from GitHub, the Great Scott Gadgets organization, Facedancer repository, and then in Facedancer examples we'll have some scripts, and these all do different things. I'll take you through some of them. The one that's usually fun to play with, first of all, is called Rubber Ducky, and this, you can have a look at it. This just emulates a keyboard and types some keystrokes, and so this is, like something you could just plug into a host and have it automatically type some stuff. So let's give that a try. And to do that, we need to plug in the target side. So I'm going to plug this in to the same computer for now. So we'll be, running Facedancer and feeding that back to the same computer. So I'm going to plug this in on the target C port. And this cable is going to the same computer, and then I'm going to run this Rubber Ducky script. And when I do, you'll see it's going to show up as a non-suspicious keyboard, and then it's going to start typing all by itself, and we can see we can use that to plug this keyboard in that automatically runs a command on the system. So that's a sort of example of the kind of things you can do with Facedancer. And there's lots of other code in here you can use as well to do things like emulate a mass storage device, so like a flash drive. You can emulate like FTDI serial devices, and or you can write your own USB devices. So if we look at this minimal example here, this is an example of how you would write a USB device in Facedancer, and it's pretty straightforward because it's all just done in terms of these classes. So we have a USB device class, and you can subclass that to define your own device, and you specify things like the product string, the manufacturer string, all of these things that we've seen when USB devices enumerate. And within that you can set up configurations, interfaces, endpoints, just as more classes, right? So it's quite straightforward, and then when you want to make these devices do something, you do it by writing these handlers, which are just functions that respond to some request from the host, or to when the host asks for data, or things like this, and you can just fill in what you want to do, what you want your code to do when the host does that. And if I run that minimal script, we'll see that enumerates, it comes up as this example USB device, and so on. So it's that easy to create USB devices with Facedancer. Now, if you'd like a more detailed introduction to this, if you look in the Cynthion documentation, there's a tutorial on emulation of a USB device. This one walks you through emulating the Hacko F1, which is another Great Scott Gadgets product, just enough for the host to be able to detect it and think that there's one there. And so this goes all the way through how to do that. You can follow that example if you're interested. But what I'm going to do now is just jump straight into how we're going to emulate this PlayStation 5 controller, which is what our aim is in this series. Now, to find the information that we're going to need to start emulating this device, let's come back to this. This is the very first capture that we took of plugging the controller into the console. And we can see all of the requests in which the host is learning information about the device by asking for its descriptors. And all of that is then gathered up into the device view over here, so we can see how that corresponds to the structure of this device. Now, the first thing that gets fetched is the device descriptor. It's 18 bytes, and that corresponds to all this basic information about the device that in Facedancer you would set as fields on the USB device class. Now, as a really nice way we can pull this stuff into Facedancer, we can just save this descriptor to a file. I'll call it device.bin. I've already saved that actually. And we can then pull that into Python. So we can read that file in, and now we've got these 18 bytes, and if we pull in the Facedancer classes, then we can make a USB device from that binary descriptor data. And if we look at that device, it's got various things set, and we can see that the vendor ID and the product ID and everything have been set accordingly. There's another really nice thing we can do as of Facedancer 3.1, this is something I've added, is we can ask that device object to generate the code needed to reproduce it. So it's going to help us write our script for us. Right? Now we can see we've got all the same information here that we had in the device descriptor here. One thing we don't have is these strings, right? Because what's contained in the device descriptor doesn't include the strings themselves, it includes references to them. This just says manufacturer string is string number 1, and then later the host comes back and says, okay, give me string descriptor number 1, and it reads that it's Sony Interactive Entertainment. Right? So we can take this a step further by adding information about the string descriptors. If we define our strings to be these ones that we saw, we can recreate this device and give it those strings as well, and now when we generate the code it will include those as well. Now, next thing, a device must have at least one configuration, and here we've got just a kind of placeholder configuration, but the configuration that we saw in the device that we captured is a lot more complicated. It's got 4 different interfaces, 2 of which have alternate settings. Each of those interfaces has endpoints, there's other class specific descriptors attached to them. There's a whole lot of stuff going on here. But all of that information is fetched by the host in this request, where it asks for configuration descriptor, and what it gets is not just this configuration descriptor here, but all of the other stuff comes attached afterwards. It fetches 227 bytes of data that represents this whole configuration, all the hierarchy under here. So if we save this control transfer payload, we'll just call this config.bin, and come back to Python, we can read that in. We've got all those bytes of data, and again we can create a object from that binary data, and again that knows how to generate its own code. So here is all of the Python code that we would need to write in the Facedancer library to reproduce that configuration. You can see the same structure here. We've got the configuration, we've got interface 0, interface 1, and then the alternate setting version of that. We've got the endpoints in there, we've got the class descriptors. All of that's in there. We can take our device and add that configuration to it. And now if we print the code from the device, it includes this device definition, but that configuration nested inside it. So this is a really powerful capability that we've just added to Facedancer in release 3.1, where you can use the ability to construct these objects from binary data that you've captured, plus the code generation, to write most of the code that you're going to need to emulate this device for you. So there's still one more descriptor I want to add here. And if we come back to the capture and just scroll a little bit further down, we will see that there's this descriptor request here where it's asking for the HID report descriptor for interface 1.3, so the human interface device interface. And that descriptor, we talked about it a little bit last time, this is actually what tells the host how that human interface device packs its data. So we've added a little bit of decoding for this to packetry since then, so you can actually see the decode of this descriptor here, and you can see it defines an input report of 64 bytes with the different axes in the first few bytes, the hat switch here, the buttons, and then but a lot of the stuff in here is just marked as vendor usage. So remember when we were looking, we were seeing where the motion sensor data was. All of that is just defined as vendor usage. There's also an output report definition in there. So we need to have this descriptor as well. So again, we can just save the payload from that request to a file. We'll call it report.bin. And in Python, we can load that data, and again it's just some bytes, and we can create a descriptor from the type number for a HID report descriptor, the number that it's being requested with, which was 0, and that data. And just like I showed you with devices and configurations, we can print the code that descriptor object generates for itself, and that is what we would need to add to our script to declare it. Now we can also attach that to the right place in our device structure that we've got. So we've got our device, its configurations. In configuration 1, we've got interface number 3 with alternate settings 0, and we can say we want to add the descriptor to there. And now if we print the code generated by the device, that will include that descriptor. You can see it here in the right place attached to interface 3. So we've now got all of our descriptors declared. I'm just going to write this code out to a file. So I'll just tell the print to write it to emulate.py. So now that we've written out that file, let's open it up, have a look at it. And so here's all of that code that's been automatically generated. And there's just a couple of things we need to do to make it possible to run this. We need to import the various classes that we need, and we're also going to import the Facedancer main function. And then at the end of this script, we're just going to call that main function with the name of the class that we're going to use here, which is this device class that we've declared. And so that's ready to run. But what I'm going to do, rather than connecting this to the console initially, I'm just going to connect it to Linux, and I'm going to compare what happens with our emulated controller here with what happens when we plug in the real one. And so let's just watch the kernel messages here. And I'm going to connect the real PlayStation 5 controller, and we'll see what comes up. Now, Linux has full support for this controller. There's a kernel driver that was contributed by Sony called PlayStation, which supports, I think, all the generations of PlayStation controllers. And you can see this comes up and creates input devices for the motion sensors, for the touchpad, and the gamepad itself. And for instance, if I just move my finger on the touchpad on the controller, you can see that's moving my cursor. So that's all working. And so let's try that again. I'll disconnect the controller, and this time I'm going to connect up the target side of our Cynthion, and we'll run this emulation script. So you can see it's tried to set up this device, but we've got a whole lot of errors here, which come up in red. But it has recognized it as a device, it has assigned the PlayStation driver and so on. But you can see that it's reporting errors because it's failed to do various things. And this makes sense because so far we've only sort of declared all of the descriptors of this device. We've described, how it should present itself, but we haven't implemented any behavior. We haven't given it any code to tell it how to handle requests. And so we're going to need to add that. And you can see over on the Facedancer side, we've got all these messages saying that it's stalled unhandled requests, i.e. it didn't know how to handle them, so it's returned an error to the host. So this all makes sense. Now, how can we figure out what we need to do to add these handlers? Well, there's a really nice feature we can use for this. If we run this script again, but add the --suggest option, which is a built-in feature of that Facedancer main function, then it's going to do the same thing again, but it's going to keep track of what requests it got stuck on. And when I stop that script with Control-C, it's going to print out this. It's going to say, right, automatic suggestions. These are things that were not implemented that the host asked us for, and it's giving us sort of placeholder code that we can drop into our script that's already tagged with the right request numbers and telling us which interface we need to put these on. And there's some comments in there telling us, how much data was the host asking for, or what was the data that was sent to it in the case of an outbound request, and so on. So this really helps us get started. So we can take all of this, which is to be attached to interface 0, and if I edit the script, find interface 0, and we'll just put this in here and just make sure we've got it all correctly indented. And so that's our placeholder functions that we need to fill in what we're going to do. And so by default this is just going to store these requests, but we can replace this code with something that we say does request reply and send some bytes back. We'll do the same thing for the ones for interface 3 here. So just find interface 3 and put those in here. And so that's the handlers that we're going to need to write to stop it getting these errors. Now we still need to figure out what we're going to send in response to those, but again we can look at our capture for that, right? So we've got, for instance, here this class request 10 here on interface device 1, interface 3, and what happens here? It asks for something and we just send back an in transaction with no data. So looking back at the code, yet we have a request 10 on interface 3, and okay, so rather than stalling that, we could just reply with no data, right? And so now we've implemented one of these handlers. And we can do the same thing for all of these just by looking at what the device is doing when we captured it and filling in that behavior in our code. And because these are class requests as well, the meanings of these aren't a mystery as well. We can also go and look at the documentation from the USB IF for these different classes. So these ones are the audio interface. They're defined in the USB audio class. And these ones down here in interface 3, this is human interface device, so these requests are defined in the HID class specification. So there's documentation you can go and look at to find out what these things are doing. And also we've got our kernel messages here, so we can see that this message here is it was trying to retrieve DualSense pairing info, it was trying to get the MAC address, things like this. So we get clues from the host software as to what it was that it was trying to do, and that can help us understand the information we've got in our captures of what data is coming back. So I've shown you how to get started here, but the details are something that you've got to work out for yourself for a given device. But in Blue Peter style, I've got, here's one I made earlier. This is a version of the script where I've implemented these requests. There was a bunch of different requests I needed to implement for the audio class to fetch or set different parts of the audio state controls on different fields and entities. And down in the interface 3, I've got handlers for what turned out to be the HID set idle function and the HID get report request. And here's some data that I've just copied from what was seen in our captures. And if I run this version of the script, then up this pops, no errors, and it matches what we saw with the real device. So we can get this far. We can fool Linux into thinking we've got a real PlayStation 5 controller here just by writing really what's just 5 functions, having had all of the rest of the code and the boilerplate for this written for us. So this is a really powerful capability, and this has got us up to the point where now we can start thinking about returning data from this controller. And we can start thinking about how we're going to replay our controller data, how we're going to generate the controller data that we want to input for what we want to do with the console. But we'll tackle that next time in the next video. So thanks very much. I'll see you next time.